All right, so today's is regularization. Interestingly, this topic used to be part of Mod 2. So because, I mean, anyone who's already gone through rigid and lasso material, you can see that it's just an extension of linear regression. And previously, when we had talked about linear regression, we mentioned checking for overfitting or underfitting. And the way you check for overfitting is for if your RMSEs are very different or your MSEs are very different, your average errors. And we didn't really talk about what do we do if something is overfit other than just dropping variables. In a similar vein, actually, like lasso regression does drop variables, but regularization is a more broad term for reducing overfitting in any model. So that's what we'll be going over today. Before we start, last call for questions.
Could you remind me what overfitting means again?
Yeah, overfitting basically means when your model has overlearned your training data in a way that your model becomes unable to generalize to unseen data. So usually when you're creating predictive models, prediction models or models used for prediction, you are training it with data that you know, with the idea of taking your model and using it to predict on unknown data. And if your model,
I remember the diagram of where the line kind of matches the points too precisely. So
yeah,
once that,
like right
okay,
here, right? Yeah, so this is overfitting. It's basically when your model learns too much of your data. We're gonna like do a whole recap on this again because I think it's gonna be very important. But yeah, to talk about regularization, regularization is a general term for what you do to combat overfitting. So regularization is the umbrella term for all these methods, and it discourages overly complex models by penalizing the loss function. So remember we talked about cost function last study group where we talked about gradient descent, and the whole idea of how machine learning models work is they're trying to optimize or reduce some cost function. Loss function is the umbrella term for cost function, just in case you're wondering, but can be used pretty synonymously across Mod 3 material. So when we were talking about linear regression, we briefly talked about the bias and variance trade-off. So another way of thinking about overfitting and underfitting is also looking at bias versus variance. Basically, there is always a trade-off when you're deciding that you want bias and variance. This black curve up here is your total error. And usually for most models, there's some sweet spot where bias and variance are both at an okay level. So you can sort of see here that would be probably around this middle zone where your total error is the lowest. So you have but you're still going to have some variance and some bias just because data is so random. Another diagram to explain what bias and variance mean specifically. When you have something with high bias, you sort of have a systematic error. Like all your error is happening in the same way, in the same pattern. So you can see with this diagram here, you have low variance but high bias, but all of your points are systematically a little bit too high. That's a sign of high bias. And basically that means there's something wrong with your model. High variance, as you can see here in these two examples, there's very little precision in your model. Your model is just not very good at making predictions. Usually if your model is a little bit underfit, it doesn't really learn the intricacies of your data. You get a model with high variance. So bias variance trade-off is just another way of looking at over and underfitting. So over and underfitting can happen in both these ways. So
one quick question, Yush. Yeah. So out of this, which one will be the most apt? If we have to select one of the quadrant, right?
Yes.
One section. So which one should we select?
Well, ideally it's the one with low variance and low bias, right? But whether you prefer high variance or high bias really does depend on context. Like, would you rather have like predictions that are, let's say you're building a model that you need to make repeated predictions. In different contexts, different ones are better, right? You'd rather have, some super accurate and then some that are a little bit off. Maybe in this case, something like sports betting. because you can have some that are off, but you have like a couple that really strike and do really well. Whereas in some situations, you'd rather have high bias, where you would rather, you know you have a systemic error, all your points are off, but in the same way. That way you can kind of account for it, perhaps after the fact. So depending on what you're using your model for and the context, that kind of helps determine whether you prefer high variance or high bias. But usually you want some balance of both. But yeah, in those specific situations, those weren't even like the best examples, but some situations, actually a lot of situations, you will choose one over the other. And we'll actually, throughout the rest of this mod, talk about a lot of those situations where you're choosing one thing over the other. But yeah, so just to summarize bias and variance really quick. High bias, you have a systematic error in predictions. Like I was saying here, all of your points are a little bit too high. Bias is talking about the strength of the assumptions the model makes, and underfit models tend to have high bias. If you have an underfitting model, and let's say maybe it's just not considering one factor very well or one feature very well, maybe that's what's pushing all the predictions off a little bit. High variance. With a high variance model, it's very, very sensitive to changes in data. And then overfit models tend to have low bias and high variance. So typically when you have an overfit model, this is the kind of pattern you're looking at. And we'll talk about this more in context, so it's less abstract.
And is the same thing for the underfitting models?
Yeah, underfitting models, you could say underfitting fall under like both of these as well. Because underfitting is just a model that has failed to learn your data. So when a model has failed to learn your data, you get, it's mostly high variance just because it doesn't learn any specific patterns. And then you just get predictions that are all over the place. Or actually, you can think about like in the case of severe underfitting, where perhaps in the context of a linear model, perhaps your model is so underfit that it only, for example, predicts the mean of your data points. In that case, you have something that's high bias and low variance. It just, again, depends on the situation. So cool. We have talked about this diagram quite a few times, overfitting versus underfitting. Underfit models basically fail to capture all the information in the data, basically, as I mentioned just now, has failed to learn some patterns in the data. A lot of information is unaccounted for. Overfit models tend to fit all the noise in the data and fail to generalize, which is why overfitting will usually get you a very, very low training error, but then a very high test error. And we're actually going to look at an example later on. And so how do we know if our model is over or underfit? Train test split. If we're looking at our testing error again, for overfitting, your test error is going to be way higher than your training error. Underfit is just going to be high errors across the board. With underfit data, it's also very possible that your train error is really, really big. Your test error by randomness can also become smaller than your training error just by randomness and chance. So those are things to look out for, which is why for linear regression, I know it wasn't part of the rubric, but if you looked at RMSE for your model, it tells you a lot about whether your model is over or underfit. So typically, as model complexity increases, so does the possibility for overfitting. So as we saw, in our linear regression models, as we added features, naturally R² goes up. And I think I said it a bunch of times, a high R² is not always the best thing because it overfits to your training data and fails to generalize to your testing data. So as your...
To what extent does the adjusted R² account for that issue?
It does a little bit. It really does a little bit, but there is a formula for adjusted R² that is in the lessons, I want to say in section 18, that actually shows you the formula of adjusted R². And you'll see that it doesn't really take into account, it doesn't really take into account. It does reduce the number, but not by a lot. It just by, I think, like a factor, a small factor. But as you can, if you do run a model, for example, with like 500 variables versus like 20, the difference between R-squared and adjusted R-squared will be greater with more variables. But adjusted R-squared still fails to, it does account for a little bit, but I don't think it does the best job at accounting for overfitting. So by model complexity increasing in a linear model context, increasing complexity just means increasing more variables. For example, like, you know, if you're introducing 10 more variables, that's 10 new dimensions. And so your model just becomes more complex. So this is more of just like a conceptual recap of like the idea of overfitting. When anything is overfit, and actually a very, very common question is how do you combat overfitting? That's a common question that they actually ask during interviews. Other questions are in this realm, like what is the bias variance trade-off? What is overfitting versus underfitting? And then they'll sometimes, as a follow-up question, ask, what do you do to combat overfitting? And usually the general answer is regularization. If they're asking it in context of a specific model, there will be specific terms. So for example, for this study group, we're going to be talking about ridge and lasso. Ridge and lasso are regularization methods specific to linear regression. So later we'll actually see in other models, there are regularization methods for other models, but they're not called ridge and lasso. They actually have some other general terms that we'll talk about later on. I'll sort of allude to, I'll actually like mention them later when we talk about this. But any questions so far before we get into something more specific? All right, so to get into ridge and lasso, they work very, very similarly. How ridge and lasso work is they basically penalize large coefficients. Basically penalize, it uses the technique of penalized estimation. And I'll sort of talk about, I'm not gonna talk about like the math specifically, but I'm gonna talk about what the implications of this cost function are and how it leads to preventing overfitting. I'm not gonna dig into the, like exactly how this equation works. If you're interested, I keep forgetting to do this. I'm gonna send out a really, really good book that if you're interested, it's a textbook. It's a really good book that explains this really well. But I feel like in a 1 hour study group, not worth getting into. So basically, penalized estimation sort of makes all of your coefficients smaller so that, you know, it doesn't overlearn any specific feature. So for example, I think a lot of you in your models saw very high coefficients for, I want to say like square foot living. Everyone had like, you know, when you increase your square foot of your place by like 1, your house price increases by like maybe like 50,000, for example. So having that easy effect on your price by 1 variable makes it very susceptible to the changes in that 1 variable, right? So if your house is like really, really big, but let's say all its other features are not so great, your model is very, very easily, your predictions made by your model are very, very easily affected by the 1 feature. And so it's kind of overfit to that feature. And so that's why you want to penalize larger coefficients. So some of the penalties have the property of performing variable selection by actually reducing some coefficients to 0. And we'll talk about that later in more detail. And then also just shrinking coefficients. Questions about that? I am going to dig into this a little more. But
one question is, now let's say I'm not using lasso to penalize right, the coefficient, and I have to like just understand, and I need to just view the the report, the summary that is there, and based on the summary, if I just say that okay, these are the features which has got high coefficient, so what I'll do is I'll just remove them and select the lowest coefficient and the highest R-square. Will that work to predict a better one?
So basically you're saying that using lasso and the output of lasso, use that and feed those features into a regular linear regression?
Yes.
Yeah, you can absolutely do that. Yeah, that's actually a technique that I've seen used before. But usually, if you're using lasso and you have set your and lasso has brought your coefficients down to 0. Usually on the rest of the coefficients, it's very similar to just running a regular regression. I don't know if that makes sense.
And yeah, okay, that's one thing.
Mm-hmm.
So now when I use lasso, it becomes very easier for me to drop right larger coefficient.
Mm-hmm.
The second part which I wanted to understand, right, is like when I'm not using lasso,
Mm-hmm.
I still want to write drop variables which has got maybe high coefficient. I mean high coefficient and low R square. If I just drop those variables, will that work? Will the prediction be proper?
I'm not sure if I'm understanding your question fully. Let me think a little bit. So from your lasso, you have managed to drop some variables.
Yeah.
And you want to use the dropped variables to make a prediction? Is that right?
I want to understand whichever variables are dropped, are they the correct ones?
Ah, that's a difficult question because modeling, you're never going to be able to perfectly model the world. It really comes down to, after you drop the variables, really just doing your chain test split and testing. And only through the testing process, you'll see if you've dropped the correct ones or not. So it really could be, sometimes it could be, you know, over complexity of your model, and then lasso will help. But sometimes maybe you're just like, you know, maybe I think, again, a very, very common conclusion that a lot of you came up with was a linear model is not the best model to predict. And this ridge and lasso are still both linear models. We haven't really moved away from that yet. So if it is true that, you know, linear model is not your best model and you're still using ridge and lasso, it might help because you don't have like that overfitting problem, but you still have the same issues of, you know, perhaps a lot of your assumptions are not met. Perhaps a lot of your, maybe like a lot of your features are still not linearly related to the target. So there's a lot of like other things to consider over that, but I mean, definitely something to try. Like if we had talked about this during last mod, I would have said, you know, try a ridge or lasso model if you have a lot of variables and just see what happens. It's just part of the process. It's just another thing to try. Yeah, which I know not a good answer and not like a solid like yes or no, but like honestly in this case it's hard to say because if there was a yes or no answer, like data scientists would have no job. Yeah. But yeah, thanks for that question. That's a good thing to consider. Yeah, doing a ridge and lasso, you can really think of it as just like, you know, trying a different set of features. So yeah, awesome. Anything else? Cool. All right, I just really wanted to talk about the cost function just really briefly and about how it works. So just to like quickly dissect what's going on here, I'm gonna make this a little bigger so y'all can see. There we go. Hopefully this is a little bit better. So this cost function, this first part of the cost function is same across both of these. And it's actually the cost function here is it's the same cost function that we are using in linear regression. Here you can see that you're just taking your actual values minus your predicted values, and you want to reduce that RMSE. That's exactly the same thing we were doing in the linear regression. This is the formula that I talked about on Thursday with our gradient descent. So within this cost function, what changes is how you make these predictions. So these predictions in a linear regression were just taken by, you know, taking where the points are on the line. So in a linear regression, and let me actually annotate this super quickly. In a linear regression, where are my lines? All right, I'm gonna draw a tiny one over here. But in a linear regression, if we have like this to be our model, for any given x value, our prediction, so let's say for an x value of here, whatever this green line is, whatever our prediction is going to be that y value. So that's how predictions are made in our linear regression. So that y hat for linear regression is generated by this. Now the y hat in a ridge and a lasso is a little bit more complicated than that. So the y hat in a linear regression has 2 additional parts, or 1 additional part that is split up again in 2 different parts. The 1 additional thing that we have is, let me circle it, is this lambda. And so you can sort of see here that this lambda term is being added. We're adding this lambda term to our cost function here. So we're adding this lambda term, and what is with this lambda is m. And m, if you remember is our coefficients. Is m our, yeah, m is our coefficient. I know the letters are not consistent, but m is our coefficient. It is the parameters that we have estimated. So basically, if we have a very large coefficient, like as I was mentioning earlier, like, with like square foot living, for example, having a coefficient of like 50,000, that will add 50,000 to your cost function. And so adding 50,000 squared to your cost function is going to bring your cost function very, very high. So your model is going to readjust such that you don't have any high coefficients. So that's kind of how the cost function works, and that's how it's reducing. Your magnitude of your coefficients. Questions about that? All right, and in a lasso, it's actually exactly the same function. The only difference, instead of squaring, you're taking the absolute value. And the difference between ridge and lasso is just the squared here. Implications of that is that, because you're squaring your coefficients here, none of your coefficients go down to 0. But given that you have the absolute value here, if you work out this function here, there is a possibility for your predicted coefficients to go down to 0, which is why lasso can be used as a feature selection tool. As we were talking about earlier, I hadn't really talked about it or hadn't really introduced it yet, but lasso can be used as a feature selection tool, because if you run all your data through lasso, some of your coefficients will actually be brought down to 0, and you can basically not consider those coefficients at all. Because if you remember, having a coefficient of 0, that was our null hypothesis in our linear regression. For each variable, the null hypothesis was that there is no relationship, the coefficient is 0. So bring coefficients down to 0. If you have a 0 coefficient, you can pretty much disregard those variables. And basically, if you're considering less variables, you have a lesser tendency to overfit. So see that connection over there? Awesome. Questions so far? I think if you're really, really interested in this, and if you do end up using a ridge or a lasso, we're not going to do it in this project for this Mod 3 project, but if you decide to do another regression project for your capstone, definitely try ridge and lasso. And if you do end up using a ridge or lasso model, I will really, really recommend that you learn how that model works. All right, so so I have a question here. We're penalizing large coefficients. So what are the effects or implications of that? Like, can anyone see how that could be an issue if we're not considering other things about our model or about our features? I mean, we have a little bit of the answer here, but anyone want to like verbalize these thoughts?
I guess if some variables have very large units, like, I don't know, maybe like square feet with the for.
Yeah, absolutely. All our variables exist on different scales. So with square feet, we were getting like coefficients of like in the thousands. With like bedrooms can only range between like, well, I guess in that example, it was like 1 bedroom to, excluding that 33 example, I think it was like 1 to 8 bedrooms. And so having your bedrooms like capped between 1 and 8, but you have square foot ranging from like, I think it was a few hundred to like what, 70,000 square feet was the max, I think. So just having all of your features on different scales, naturally you're going to get very different looking coefficients, because the relationship, you increase 1 in bedroom is going to have a much bigger effect in price versus changing this, versus adding 1 square foot to your house. I know not everyone's model reflected that, but generally that's what you want to think of. if you're
This is
adding more.
exactly why I wanted. This is exactly why I wanted to test. I mean, whether dropping a higher coefficient made sense.
Mm-hmm. Yeah. Yeah. So that's why we are going to next talk about standardization. So when you have a higher coefficient for something that is like bedrooms, that for those of you who kept bedrooms as a continuous variable, having a high coefficient for bedrooms, what does that mean in context versus looking at a high coefficient, something like square footage? Because, you know, square footage ranges from like, again, like 3 digits to 5 digits, where bedrooms are still like 1 through 8. Looking at their coefficients together and comparing them on the same scale and using them in the same cost function that way, you're going to be, yeah, again, you have features on different scales. And so naturally, the coefficient for bedroom, you would assume, would be a lot bigger, which is why we have standardizing our data. I know that while we were doing our linear regression, standardizing our data, as I had mentioned, doesn't really change the distribution of your data. But I did say it helps with, you know, comparing apples and apples instead of apples with oranges. Basically, what standardization does is it will take a look at, you know, your 1 bedroom increase impact on price versus your 1 square foot increase on price, and sort of bring them to the same scale. So if you standardize your data, your feature set will, not feature set, the range of each feature will be perhaps between like 0 and 1 or -1 and 1, so that a change in 1 will have the same, the change in 1 impact, sorry, the change in 1 of any of your features will result in a level change in your price. Does that make sense?
So to be clear, are we talking about like percentage wise? So suppose you have like 1 bedroom to 8. So like a 1 bedroom would go up, I don't know, 20%, I'm not less than that, like 15%, something like that. And then so also with the change in square footage would be like percentage wise that way. Is that how you're looking at
That's a really good question. Typically, it's not looking at percentages. The percentages change is actually more of when you're doing, oh, wait, sorry, I misunderstood your question. So you're saying that by standardizing, we can look at it as a percentage change rather than an absolute change?
Yeah.
Let me think.
That's what I'm saying. Is that the purpose of it? Because it would make, I mean, to make sense, I don't know if you want to say it's going up 1 unit, but a bedroom can't go up the same unit as a square footage unit. You know, as it was making it percentage wise, it makes it as 1 unit basically.
Yeah. Yeah. Actually, I think that's a good way of thinking about it. Yeah. I was thinking of it from a different perspective, but yeah, that's kind of a good way of thinking of it, because yeah, increasing 1 bedroom is not the same as increasing 1 like square foot. So yeah, doing a standardization helps you level out those 1 increases across different variables.
Okay, cool.
Awesome. Yeah, that was a good clarification, I think. So yeah, if you have features on different scales, some will get unfairly penalized. And so there we have it. As I mentioned before, a downside of standardization and why I didn't really recommend it to a lot of you is that the value of coefficients become less interpretable and have to be transformed back. So any of you that tried like normalization or like any sort of standardization had to deal with that. If you want to interpret how 1 unit change in a feature impacts the target variable. And I think a couple of you dealt with that. Something that I didn't talk about, just because it wasn't introduced in the curriculum, is when y'all were doing scaling, you would write functions, or you would just do it straight in pandas. You would just like minus the mean, divide by standard deviation. Something I didn't talk about was that there are actually built-in methods in scikit-learn to do the scaling for you. I have the documentation linked here, and I will talk about it as we walk through the code. But any questions about this standardization step yet?
Just one, like, would it be right to understand that while the standardization is happening, it considers the mean or the median for actual calculation?
Yes, yes. Standardization, I mean, when you standardize, you're always going to consider the mean and standard deviation of your data. If that was what you're clarifying, that's yes.
Okay.
There are these built-in methods that make standardization and unstandardizing a lot easier. So I'll talk about that when it comes to those points in the code. So this next code steps, there are a few syntactic things that I wanted to point out. The scalar being one of them. I also wanted to talk about like some of the arguments in some of the modeling code. So that's why I have this here. But this code, in summary, what I'm going to go through is the same data set with a regular linear regression. And then we're just going to look at how it performs differently if we were to plug our data into a ridge and a lasso regression. So that's overall what we're going to talk about. But yeah, within that, I'll talk about some little syntactic things. All right, so here we're going to be importing a bunch of different things. I will, as they come up, I'll explain some of the new things that we're seeing here. So let's just import this super quick. What we have here is pretty much the same thing that we've done before. Reading the CSV, here we have housing prices. It's a slightly different data set. So actually, let me just show you all what this data set looks like. There we go. All right, so this is the data set. I'm honestly not too sure where this comes from, but this one actually looks at lot areas, similar to what you're doing with your projects. This one also has, like, if you have a pool, if you have, I think, the quality control of your pool, fences, all sorts of different things. So this one has a lot more features. This by itself, before even making dummy variables, already has 81 columns. So this is what this data set is, and we're just going to fit a linear model to this data set. What we're doing here, this is code that I took from, I took this code from the lessons, so you might come across this again, but I don't think the lessons talk about some of the specific syntactic things that I really wanted to point out. So we have the data set here. What they're doing here, I think first they split up the continuous and the categorical variables, very similar to what a lot of you were doing. So first, they're working on the continuous variables. So here's actually something that I remember one of you had brought up when we were first introducing the project about data leakage when you're filling in null values. And by using this simple imputer, we can talk about how that works across the train set and test set. So just to recap, when you do a train test split, and I actually talked about this with scaling, when you scale a variable, you should only scale it using the parameters of your train set. So if you were to normalize a variable, for example, you want to normalize your square foot, you should be using the mean and standard deviation of your training set, not your entire data set. That's because, you know, if you include your entire data set, it's taking the mean and standard deviation. That's taking into account data that you're supposed to leave as unseen. So therefore, to prevent that data leakage, you're only gonna scale based on your train set. And I remember someone talked about, all right, if we're imputing with like median or a mean, wouldn't that have the same effect? If we are imputing our null values with like the mean of the entire set versus just the train set. So here is an example of showing you how you would impute the mean or median with the values from the training set. So how you do this, there's actually a scikit-learn simple imputer, and you have different strategies. Actually, I don't have it linked here, so let me look it up super quick. And basically, you can see that for a simple imputer, it will replace null values with different strategies, and by default, it's the mean. You can also tell it if it's looking for null values, if you're looking for a specific like string, because sometimes you have like, for example, I think in one of our project examples, there were like a string of a question mark for null values. You can also take those into account. And you can basically tell it how to impute. So you can talk about mean, median, most frequent, or some like constant value, and a lot more other parameters that we won't really talk about. So with this simple imputer and a lot of these scikit-learn things, we always have to first instantiate the object. This this like concept of instantiating something first is something that we'll actually get more into detail when we talk about object-oriented programming at the end of the mod. But as you can see here, first you're telling the simple imputer, all right, this imputer, imagine that you're like building a tool to impute things. You're building this simple imputer to impute whatever it is with the median. But at this point, it doesn't know what the median is yet. It just knows it's going to look out for the median and fill it in accordingly. So what we do here, this is after train test split. You can see here there are two lines that we're using the impute. So first on the train set, we're doing a fit transform. And so what that's doing, it's actually imputing the data. First it's fitting the data. So it's first finding out what the median values are and then doing the transform. You'll see this fit transform come up quite a bit, but fit and transform basically, one looks for the mean in the fit stage and then transform imputes the mean or median accordingly. So this is imputing all the null values for the train set. And for the test set, as I mentioned, because you should be filling in the test set with the average values from the train set, here instead of doing a fit transform, you're just doing a transform. So what's happened here is that when you were doing like the fit stage of impute, impute basically learns what the median is and then just transforms it accordingly onto your test set. Questions about that? We'll see this happen again with the scalar actually in a little bit. But questions about this syntax? All right, so you're always fit transform on the training data and transform on your test data. So this step is just filling in those null values. Moving on, everything's all in one cell because I wanted to speed through this. Categorical variables, creating the categorical variables, filling the null values. And this is another example of how you're scaling. So something that I didn't bring up before, but scikit-learn has built-in scalars. And here you have the standard scalar. So standard scalar just standardizes your data. And again, first you are instantiating it. You're building the tool. And then you're going to fit transform it with your train set. And then just using the train parameters that it's learned in the fit, transforming your test set. Cool. All right, I think this is not a model that we want to use, so I'm going to ignore that for now. We're going to one-hot encode. I think they're just like combining all the data together, and we're going to use all of this data and plug it into a regression for now. So this is just taking the X train, and they've done all of these. Doesn't matter. Just overall, what you have to know is they did scaling and they did categorical variables, and we're just going to throw that into a baseline model for now. And you can see here doing X train all. It includes your imputed and scaled data and your categorical data. And we're going to fit it to Y train. So really quickly, you can see we have our metrics here. Our training R-squared is really good, 0.936. Really, really high R-squared, fit our training data really well. But you can see here our test R-squared is actually negative. And I don't know if anyone's seen a negative R-squared before, but a negative R-squared basically means that it's fitting even worse than just guessing the average. Because if you remember what a R-square is a proportion of how well your line is fitting the data compared to like the average line across. This is saying that this prediction is even worse than if you were just to predict the average value across all of your data, all of your test data. So that's really, really bad.
Yish, now this negative R-square, I actually faced it in the the renovated, when I had modified age of renovation where I had minus, in that I actually had faced this issue of negative R-square. But then I realized that maybe it was only because it had negative values. But then it's not necessary, right?
No, it's not necessarily due to like negative values. It's just probably, usually negative R-squared comes from, most of the time that I've seen negative R-squared is when your data doesn't meet the linearity assumptions. So if you have data that's super not linearly related to your target variable, you do usually get a pretty low and sometimes negative R-squared because of that. If it's in your training R-squared especially, that's when I've seen it the most.
Okay.
But I don't know if that was the case for yours.
No, but then that was my assumption, so I just left it accordingly.
Yeah.
But yeah.
Yeah, that's fine. With modeling, you just try a bunch of different things and see what sticks. So yeah, you can see here our errors are awful. There's mean squared error here, but our training mean squared error for a house price is only 20,000 off, which is great. But our testing error is even more than like the cost of a house, I think. So this is a classic case of really, really bad overfitting. Questions about what we've gone through so far. Main things to point out here is we've talked about the difference between doing a fit transform and a transform and how it stops data leakage, and how it also saves the information. But yeah, this is not too much of this other stuff in terms of procedures. It's not new to y'all. One thing to mention, with this scalar, you have fit transform. What's really cool about this, and I think I have it linked here. So if I go to standard scalar, and all the scalars have this as well. If you look at the documentation, see you have fit transform, because you can fit without doing the transform as well. Fit transform, transform. The other one that's going to be useful would be inverse transform. So with the inverse transform, you can scale your data back to its original values, which will make your life a lot easier. You don't have to save the mean and standard deviation somewhere to reuse. So just so you all know, in the future, if you use a scalar, this functionality is here. All right, so we talked about the regular linear regression, and we found out that, all right, this is super overfit. I mean, we can also go through the same processes that we did during our project. We can do like, maybe there's a lot of high P values. I have no idea. Maybe we can like drop and test on different subsets of data. But if we want to streamline our process, let's just try some regularization methods. So here we're going to do lasso first, and then we're going to do ridge. So lasso, and here I have a comment that lasso is also known as L1 normalization. So if you ever hear of the terms like L1 or L2, the difference between L1 and L2 being that if you remember ridge, in a ridge regression in the cost function here, it was squared. So basically in other models, you can also have L1 and L2. So ridge is an lasso is an L1, ridge is an L2, and that's talking about just like the power of the coefficients that are with the penalty term. And the penalty term here is lambda. So back down to our coding. Again, you'll sort of see, and this is going to be a pattern that's a pretty common pattern, that you can actually run all of this code without understanding what and how the model works, which I mean, great for budding data scientists, but again, I hope that over time we all learn all of these models. But yeah, the syntax exactly the same as linear regression. So if you remember the standard linear regression, where we're doing it here, we're instantiating the linear regression model, and then we're fitting the model just like that. So in exactly the same way, we're going to instantiate the lasso regression, and then we're going to fit our training data. So this has already been run, but let me run it again real quick. With lasso, you can see that train R squared still pretty high. Test R squared this time pretty high as well, not too bad. We have our training MSE, and actually let me just quickly square root that so we can see it in absolute terms. There we go. Our training MSE still 20,000. Our test MSE a little bit worse, but a lot better than our regular learning model. As you can see, like the data that we use here is exactly the same. We are using X-train all in Y-train. Here also X-train all in Y-train. And just by using a different model, we have improved our training error by just so much. Questions about this? All right, so syntax is the same. The next thing I wanted to introduce, and we actually will get more into it with other models, is the idea of hyperparameters. So different models will have different hyperparameters. Let me just quickly open up lasso. So with a model, and in this case, we're looking at lasso, all of these, or most of these, are hyperparameters that you can actually change and adjust just to see how it will work. So as I mentioned, the new thing about ridge and lasso is this penalty term of lambda that will adjust how much your model accounts for overfitting. In this model, actually they put it right at the start. In this model, and I hate that they use alpha because alpha is used for so many different things, but alpha here is a constant that multiplies the L1 term, and it defaults to 1. In this documentation, it actually shows you that if alpha is 0, it's equivalent to regular OLS solved by linear regression. So alpha equals 0 means that there is no regularization happening. And then, of course, they say using alpha equals 0 with lasso is not advised. But then you can pretty much give it any value of alpha to just account for, do you want to regularize it more or less? So by default, alpha, which is lambda, was set at 1. And that basically multiplies it by 1. And you can see we have these kinds of results. So alpha is actually a hyperparameter for this model, something we can test different amounts of alpha to see how it affects, just how it affects our testing results. And over the course of this mod, we're actually going to be testing and changing hyperparameters of all our models, which is why I wanted to introduce it here. So with this lasso, as we saw, default alpha was 1. Now let's just try alpha equals 10, just to see what the effect is. So running this super quick, and again, let me just square root this. I don't know why there is no built-in root mean squared error, but taking the square root of this, we can see that our testing, by changing our alpha to 10, our testing R-squared actually got a little bit better. I will say that it will take much more extensive testing to make sure that it is like a pattern and not just through by chance. I will say like cross-validation is good for this. If you want, you can even like plot a graph with different alphas and different errors. I do think that's what one of the lessons does. And that's part of the hyperparameter tuning process, which is why I say like a lot of data scientists just run a bunch of models and just see what happens. This is part of it. You can basically like set up all your code to run lasso from like alpha from like 0 to 100 and then just see how it gets better or worse, and then just decide on what your best alpha is. But overall, lasso, you can see no matter what your alpha is, really improves your testing error. Cool. And just to evaluate, because we know that lasso brings coefficients down to 0, let's just do a quick check to see what it's done to our coefficients. Here, I just really quickly took out the coefficients from here. And I don't know if anyone has looked into this. I think some of you did with your projects, that within lasso, you have your parameters, but you also have your attributes. So attributes, basically, that's how you get your coefficients. That's how you get your intercept term. So if we go back to our notebook, I basically wanted to look at the total number of coefficients, which in this case get close to 300. And then I wanted to look at which coefficients were very small. And for very small, sometimes it has, because of the many decimal places, I just set it to less than 10 to the power of -10. And 77 of those coefficients went down to 0. And so in actuality, I could take out all 77 of these coefficients and just rerun it again. One, it will make the running a lot faster because it doesn't have as many dimensions to calculate across. But also, you know, based on these results, you don't need these 77 coefficients. You can also like adjust and create some threshold to drop your coefficients by, but that's also part of the modeling process. Questions on this so far? Great. Just really quickly talking about ridge regression, pretty much the exact same process, the same code, the same code, just instead of your coefficients dropping to 0, they don't get dropped to 0. For this, running this, you can see that very similarly, you have reduced your test error by a bunch. And here you can see your training mean squared error has actually gone up a little bit because, again, you have that bias variance trade-off. You want to trade off some of your overall accuracy to account for or to give room for less overfitting. So you're doing that. You're sacrificing a bit of your train MSE to get your test MSE better. So yeah, another example of this. Just some overall benefits of using Ridge and Lasso. You might have noticed here that I didn't check any of my linearity assumptions, especially multicollinearity. One thing that's really, really awesome about both Ridge and Lasso is they both help take into account multicollinearity. So just to go over these bullet points that I have, for Ridge, instead of getting rid of coefficients, you're just reducing them. So if there's any reason that you don't want to get rid of any coefficients in your model, but you still want to account for overfitting, you might use Ridge instead of Lasso. So let's say your model is overfit, but you still only have like 10 features, and you don't want to lose any of them, maybe use Ridge instead of Lasso, because Lasso might get rid of some of your features. So the really cool thing about Ridge, and Lasso does this too, if you have high multicollinearity, the coefficients are actually spread across your different variables. So remember how I said before that if you have multicollinear features in your linear regression model, you have some redundancy, because the relationship is the relationship of one of your multicollinearity features is going to be taken into account. It's going to be doubly taken into account if you have two that are correlated to each other. With Ridge and Lasso, you actually spread your coefficients across both, so you don't have this redundancy. Quick downside is if you have a lot of features, it becomes very computationally expensive. So you might notice that like in a Ridge regression, it takes a long time to compute. Again, like honestly, 200, 300 features is not the most that I've ever seen. I'm not even sure how big this data set is. Let me just see how many rows this is. So let's just take a look at wide train. So yeah, this is only 1,000 rows. So I bet that if you were to have like, I don't know, in the 5-6 digit numbers of rows, Ridge regression will take a long time to run because it's doing the gradient descent across every single feature. Why that wasn't the case for linear regression is because, as we saw for linear regression, there are easier ways to come to the solution. Instead of doing gradient descent for linear regression, you can actually do, like, for example, the matrix method, or the computing of, like, you can get your slope by calculating, like, I don't know, there were all those formulas that were given in those lessons by using the mean of X and the mean of Y and all of those. So linear regression has a best solution, but for Ridge and Lasso, they have to do this gradient descent process for all different values of your coefficients, which is why it can be very computationally expensive. Finally, we had talked about this already, but with Lasso, it's great because it can reduce the complexity of your model by just cutting out a bunch of features. Like in the case here, we reduce the number of features that we need to take into account for this model. And also, same multicollinearity is dealt with in Lasso as well. So overall, Ridge and Lasso are just extensions to linear models. If you're doing a linear regression in the future, definitely consider Ridge and Lasso as well. And in a more big picture thing, regularization helps with overfitting. We're going to talk about some other models throughout the rest of this mod that have this regularization component that we will also play with. But cool, that is all I had for you guys. Does anyone have any questions? Awesome, perfect. Well, just to let you know, Thursday we'll have a study group on logistic regression, which will be our very first classification model. And classification models will be like the theme for the rest of the mod. Again, for those of you who don't know, I think all of you I've spoken to already, I won't be around next week and the week after, but all of the study groups will be accounted for. I will put up basically who's covering what and what to expect in a big Slack message, probably in the next couple of days. And in addition to that, because I won't be able to do one-on-ones, there will be additional office hours just to take any questions that y'all have. They will be all at the same study group time, but just on different days, and I will post info about that as well. If anyone has taken a look at the class calendar, that information is already there, but I will summarize it all in a Slack message in the next couple of days. But cool. Any other questions to wrap up? All right, well, in that case, I hope you all have a good rest of your night, and I will see you at one-on-ones or on Thursday. All right, bye, everybody.